P3, day 13 of calculus. Today we're going to talk about some of the properties of the fundamental theorem of calculus. So first is the one where you can break apart an integral. You can break apart an integral. So this one goes from a to c, and what you can do is you can take a number b, and it doesn't have to be between a and c, but as long as these are the same, you can break them apart. And keep in mind you can go backwards and forwards on this. So just for example, let's say, just making something up here like 0 to 8 of f of x dx. You can pick any number you want, any other number you want, and it still works. So how about, remember we have to keep a the same down here, so we'll keep 0 there, and let's go to a new b value, say, I don't know, 4. And we'll do f of x dx plus, and it has to be the same here. Notice it has to be b and b right there. So we have 4 and 4, and it has to end with 8, the same number it started. They end the upper limit of integration over there. So you can break it apart. Keep in mind though, remember that this number does not have to be between it. This still holds. I could make it instead, let's say 100. Still works. Still works. The next rule allows you to factor out a constant. So C is a constant. C is a constant, meaning it is just like a number like 7 or 8 or 12. You can factor it out in front, meaning let's say you had the integral of 2 to 8 of x squared dx. Let's say there was a 7 there, of 7x squared. That's equal to 7 times the integral of 2 to 8, from 2 to 8 of x squared dx. You can factor out constants. And then over here, if you have the integral of two functions added together, you can do them separately. Sometimes it's going to be easier to calculate integrals separately. So for example, let's say I had 1 to 9 of x squared plus x cubed dx. That's the same thing as doing the integral from 1 to 9 of x squared dx and adding to it the integral from 1 to 9 of x cubed dx. And the same thing happens if that is a minus sign. That would just change to a minus sign. So for this question it asks, write a single integral expression that represents the area between these graphs. So you have f of x equals x, and you have g of x is equal to x squared, and we're going from 3 to 5. Let's draw a picture of what this looks like first. Remember, it doesn't have to be hyper accurate, it just needs to be useful. So f of x equals x, that's going to be this right here. F of x equals x. But what about g of x equals x squared? Well, it's going to start here at 0, and then it goes up like this. So there's g of x is equal to x squared. Where do they cross? Well, that's important to know. So when does x equal x squared? Well, that's at x equals 1. So know what 1, remember this is not the scale, it's like that. So we're going from 3 to 5. We're going from 3 to 5. So 3 to 5, 3 is going to be over here, and 5 is going to be here. So the upper function is going to be the blue one. So if I wanted to make this more to scale, shrink it down a little bit, we keep on making this go up here, and f of x keeps going. And let's just say 3 to 5 is, let's say 3 is there and 5 is there. It's going to keep on going up like this. So what region are we looking at? We're looking at this region right there. So what's the upper function? The upper function is going to be the g of x, and the lower function is going to be the f of x. It's getting a little busy in there, but do you see that region right there? Right there, from x equals 3 to x equals 5. Remember, it's not perfectly to scale, but we just wanted to check to make sure the blue function's on top. So what's that going to be? It's going to be the integral from 3 to 5. What's the upper function? Well, g of x minus the lower function, which is f of x dx. And we can plug in the functions now. You have the integral from 3 to 5 of upper function x squared minus x dx. And all we've done is we've written a single integral, and that's what it wants us to do. We wrote a single integral. What we're really doing is we're finding this whole area all the way down to here, but then we're subtracting out the base area right there. So it doesn't ask us to evaluate this. We're just writing this as a single integral, So you notice how I drew it not really to scale drawing right there, but it was useful to understand what we were trying to do. The reason is if you draw this to scale, it looks like this, and that's not even the full window. This is all the way over to 3. If I change this window to go to 6, we're really looking from 3 to 5 for x, and I change the y value to go all the way up to 30 because 5 squared is 25. I'll go a little bit beyond that. It looks like this, and our calculators aren't super high resolution. Down here in the bottom left, x squared is below x, but it's not super nice. But that's what it would look like on a scale drawing. There's 5 right there, and there's 3 right there. So you're looking at this area right there.